With like underline, apparently it was 3, because when it does take the first value, it just does it accordingly. So it's like 1 plus, so it's 0 plus 1 plus 1 plus 1. So it's just weird.
Alright.
And then I did the other full I forgot to do it. Apparently it's like there's supposed to be but there's not
So we have a midterm coming up. So let's solve a few more problems like we did last time. So the problem of finding a contiguous subarray of maximum sum. We gave that problem for extra credit. It also appears in the homework that were problem set number 1. This guy here. Given a sequence of n integers, find a contiguous subsequence of the largest possible sum. So we gave an n log n algorithm way back, recursive divide and conquer. How many remember that? Okay, and we said that you could do better than that. How many found an algorithm faster than n log n for this problem? Okay. How many found linear time? That's good. Okay. Anybody want to explain how this is done in linear time? First, let's review how we did it in n log n time, because it's been a while, right? So we have an array, and we want to find a subarray of maximum sum. Maximum sum. And that subarray can appear anywhere. So it can appear at the beginning, at the end, halfway in the middle, anywhere it wants. Right? But the idea is to have a maximum sum subarray. It's too dark. Okay. So to do this in n log n time, we divide it down the middle. And when we divide it down the middle, inductively, we found the answer in the left half. In green, we found the answer in the right half in blue, the maximum subarray there. And the maximum subarray there was either in the green or the blue, whichever is larger, or it straddles the middle between the green and the blue. In which case, in linear time, you can find the subarray starting in the middle, going maximum sum to the left, maximum sum to the right, and only the maximum subarray crossing the middle. Of course, the true answer could be just isolated in the left or just isolated in the right. Try to do all this with PowerPoint, by the way. So that's one nice advantage of slides. Very interactive. And so you solve both subproblems, and then you merge the two solutions, finding the max on the left, the max on the right, or the max across the middle, and the max of all of these three possibilities is your answer, recursively, all the way down. How many get that solution? N log n time, divide and conquer, a lot like merge sort. How do we get from that to linear time? Is the next question. Yeah.
So basically, to get linear time, basically we go through the entire sequence once, as compared to linear time. And throughout, basically record two things. One is the maximum subarray ending at this position, and second one is the maximum subarray so far.
Yeah.
So to do that, basically, first I in range of 0 to L. Let's go through the entire thing. Remember we record the maximum subarray ending at this position, so we know the previous position, the maximum subarray ending in the previous position. And the new sum is the sum plus this element. And now we get the maximum subarray that ending at this position, and we compare with the recorded answer, that is the maximum subarray so far. And of course, now we have the new maximum subarray, and we need to know if the maximum subarray ending at this position is greater or equal, if it's greater than 0. Because if it is negative, we can just clear the whole thing. So then we compare the maximum subarray ending at this position with 0, and whatever is larger becomes the new maximum subarray ending at the previous position, and then we increase with it.
So, yeah, and it's correct. That's a good way to do it. How many understood what it was saying or following what it was? Okay, a number of you. That's good. So let's see how we can derive such a solution systematically rather than jump to it intuitively. So when you have divide and conquer, you can divide it into 2 equal parts, and usually that's the best. 2 equal or near equal parts makes for the best time complexity overall. Because if the division is too skewed in one direction, it's not 50-50, but rather 90-10 or 99-1, that's usually too skewed. That's the problem with quicksort. It makes it run in quadratic time, and then the partition becomes too skewed. But as far as correctness goes, it doesn't matter how you partition it. As long as you can divide and conquer, the partition if it's skewed, it's still correct answer at the end. It may just take longer in terms of time complexity. Maybe inefficient, but still correct. How do you understand that basic principle? Okay. And sometimes it behooves you to do a skewed partition rather than an even partition, even in the name of correctness as well as efficiency. And this is one of those times. So instead of having a left and right solution, why don't we have a very kind of skewed partition? Let's have the partition be everything except the last one, and then the last one. So the partition will be this. You'll see in a minute why this actually is more efficient in this case. So inductively, or recursively, you know the maximum solution in the green portion. And inductively, you also know the maximum solution that's free-floating that's the red, and then the maximum solution that's not free-floating, but that's anchored to the end. So let's say you have this solution that's the maximum sum that's anchored at the end of the green. So you know the free-floating answer in red inside the green, and in dark we have the maximum solution that's completely touching the right side of that green region. So you have two sub-solutions. One is constrained, one is not constrained. One is constrained to touch the end, one is free to move free-floating anywhere it wants, including the end, but anywhere else as well too. So obviously the red is at least as good as the black solution, right? How many can see that? Because the red is unconstrained, could be anywhere, including the end, but the black has to be attached to the very end. Okay. But let's say you knew these two solutions. How? Because you computed them recursively for the green subarray. If you knew these two solutions for the green subarray, you could very easily know the two solutions for the green subarray plus this one extra blue element that's one beyond the end of the green, one extra element. You can quickly compute the two solutions for the slightly bigger one array by one, bigger by one element, if you knew the two sub-solutions in red and black for the subarray in green. How would you do that? The new solution for the big array, including the extra one, well, first of all, let's do the easy part. What's the new black solution if you add one blue element to the end of the array. If you knew the black solution for the blue array without this extra element, for the green array without this extra element in blue, what's the new black solution there? Not hard, but silence is not an answer. So how would you compute the new black solution if you knew the old black solution and the old red solution? You add one more extra element in blue at the end there to this green subarray. What's the new solution? The one that ends at the end, including this extra new blue element.
Either it means it has to touch the last element, but the starting can change. The starting can include that element that was initially inside the black one, or it cannot.
So if the old solution, the maximum touching at the end was between this pointer and that pointer, if you add one more element, in blue, it's whatever this solution was plus this guy. Unless what?
Negative.
Unless that guy is way negative, which can drag this below zero, in which case, what's the new answer? The new answer is the no array at the end with sum zero. The zero is the identity element for addition. So again, if you have the maximum ending on the green between this and this pointers, between these two pointers, and you add one more guy at the end, the answer is whatever is the answer before plus this guy, if this guy adds anything. Because the rest of it is still the maximum going in. If the maximum was other than this wouldn't be the maximum for the green, it would still go in further if it had to go further once you add a new blue element. So adding one at the end doesn't change this end of the answer, it change this end of the answer. Right? So if this is positive, you add to it, and then that's the new max. If this is negative, it drags this down, and you're better off. If it makes the sum negative, you're better off just having the sum be zero by taking nothing. Okay? So again, adding this to this could give you the new max, unless adding this to this gives you a negative number, in which case the new max is just a nuller subarray at the end of size zero with zero sum. How many get that part? Okay, straightforward, right? So we're building up the new answer from the old answer for that array at the end. All right, what's the new red subarray with the extra new element in blue there at the end? The new red is what? Because now we have the new black. What's the new red? The one that's allowed to free float anywhere. Yeah.
So the old red and the new black?
It could be the old red. They haven't so good of an answer at the old red that it's still the maximum free floating. Or it could be the new black. Because the new black could be more than the old red. The old black is not more than the old red. It could be equal, but it could be not as good as the old red, the old black. But the new black could be more than the old red. Tell me you can see that. Because that new element at the end could have added greatly to the sum, making it way beyond what was the old red. So now we have the computation necessary to compute the new red and the new black. And now we can add one more element and pull the same trick. And add one more element and one more element. And at every moment we have the free-floating answer in red, or the edge-constrained answer in black that touches the right side of the array so far. What's the final answer when we run out of elements? Well, what do we report back to whoever called us as a subroutine?
Red.
The red. How do you see that? The red. It's at least as good as black, so we might as well report the red. How long did it take us to extend the array by one element at a time? How much time did we consume asymptotically?
saying one is constant time, right?
How many see constant time? Yeah. Because you have the two subarrays and the two sums, red and black, and to add one more element, it's you just take the maximum of the old black plus the new blue there at the end, the maximum of that or zero, if it becomes negative, then the answer is zero. It's like one if statement. It's a sum and an if. And the new red, again, is the maximum of the old red and the new black, and it's one of those two. So it's, again, an if statement, where the maximum of two things. And, keep track of the pointers, so if you want, you can also report the actual bounds of the array, not just the sum. Again, it's all constant time operation per adding new element. And there's your linear time overall. How do you get all this? End of algorithm, linear time. I don't see a sea of hands raising. I see a few. Any questions about this? Let me ask you a few questions then. How many lines of code are we talking about for this algorithm, roughly? Within an order of magnitude.
9.
A few lines, one digit, 8, 9, 10, less than 10 lines, right? Depending on which programming language you use and how you use spacing. But it's not 100 lines, it's not 1,000 lines, it's not divide and conquer, there's no recursion here. It's a single loop and a couple of if statements. That's pretty much it. That's the entire algorithm. How many see that? Yeah. That's a lot simpler than divide and conquer, recursive, calling yourself twice, solving two subproblems, and it's also faster, not just simpler, and it's less lines of code, and it's obviously correct. Question?
I have another algorithm that also I think does it in linear time that does not use dynamic programming.
Yeah.
So
There's several ways to do this, and he mentioned dynamic programming. That's insightful. How many see dynamic programming? Yeah. So this is dynamic programming essentially because you're building larger answers from smaller answers. And that's kind of the essence of dynamic programming. You have smaller answers for smaller subproblems, and from that you're building answers to larger and larger subproblems until you get the answer to the entire original big problem. But it's also divide and conquer. It's a form of divide and conquer because instead of doing the partition into equal parts like this, what we did is we did the partition into unequal parts like that, in an abstract sense. We just figured out the answer for the big part and then the answer for the little part, and we combined the two. How many see that conceptual paradigm? Yeah. And so this is an interesting example of divide and conquer where you don't want to divide into two equal pieces. You want to divide into unequal pieces. And you end up faster. And in fact, you end up with a dynamic programming approach. If you think about it, divide and conquer in two equal pieces, it's also dynamic programming of sorts. You give the answer for two big halves, and from that you combine the two answers into the answer for one larger whole, making up the two halves. So one doesn't exclude the other. Divide and conquer can be dynamic programming as well. In this case, it is. Any other questions about any of that? So this is a very elegant solution again. Any other questions about that? So again, beautiful algorithmic paradigm. Remember at the very beginning we had an n-cubed algorithm, if you remember. Look at all partial sums. For every n choose 2, begin and indices pairs. Find the entire sum. That's n squared pairs, linear time per pair, that's cubic. Then we said we can compute partial sums. So we went from a cubic time algorithm. If you compute partial sums, you can compute ij differences by taking differences of partial sums, and that gives you n squared. Right? And then divide and conquer, straightforward, two equal pieces, recursively, that was n log n. And that wasn't so trivial, especially the combining step. And finally, we ended up with linear time. And that was not just the fastest of all the algorithms, but also the simplest. Any questions about any of that? So again, beautiful algorithmic paradigm, very crisp solution. There you go, my gift to you. So that's a good day in algorithm design, when the algorithm not just gets faster, but also more efficient and simpler conceptually. And when it's simpler, there's less places for errors to hide. Truth has no place to hide, errors have no place to hide, they have no refuge. And that's good. Complexity is not your friend. Complexity is not the friend of correctness or reliability, both in codes and in machines. Electric motors are so much more reliable than internal combustion engine motors, because they have so much fewer parts to wear and tear and go wrong and overheat and wear down and that kind of thing. So complexity is not your friend. It's not the friend of good design. Okay, any other questions? You're going to solve lots of other problems. Another problem. You have a big wall. You're in front of a wall. It extends indefinitely in both directions. And you know there's a door, one door, either to your left or your right. A big gate, and you want to get to the other side of the wall. You don't know which direction it is. You don't know if it's to your left. You don't know if it's to your right. And let's say it's n units away from you. Unit meaning steps or feet or kilometers or whatever. N steps away, either to the left or to the right, but you don't know n. And you don't know if it's to the left or to the right, could be either. You want to try to find the door. What's your algorithm? How efficient is it? As a function of n, your true distance from the door, in meters or feet or whatever. It doesn't matter what the units are. It's just n units distance. So again, you have a wall, big beautiful wall, and there's a gate in it, and you try to get to the other side.
This one person needs only one helper.
You just have one person. And as you move, as you walk left or right, you're charged for the distance. That's your cost in units of travel. So you want to find the door and minimize your overall time or units of travel before you find the door. Guaranteed, worst case scenario. As a function of the true distance n, which you don't know what it is. How many have been in this situation in real life, actually? Just one person? I bet it's more. You just don't realize it. What do you think?
My application,
Yeah.
if I understand the problem correctly, it's usually me looking for a light switch in the dark.
Yeah. Looking for a light switch in the dark. So you know it's on the wall. You don't know if it's here or there because it's dark and you can't see it. So you can go one direction a long distance, but it could have been just a centimeter away from your hand to begin with. And now you went, thousands of centimeters away and wasted a lot of time, right? Give me another real life scenario. Yeah.
Like a scientist in the South Pole that gets caught in a big storm and doesn't find its way back to
You
his
get caught in a
station.
storm, you can't see, it's zero visibility. Or if you go hiking and you try to find, some way off the trail and you're not sure if it's forward or backwards, you just know there's a way off the trail and you're in the middle of the wilderness, lots of trees, you can't see very far, and this is the same scenario. Or you're looking for your favorite restaurant, you know it's on the street, you're driving down the street, but you're not sure if you passed it or didn't pass it. It could be ahead of you, could be behind you. So you don't want to drive 10 miles down the street just to find out it was a block behind you all the time when you first wondered. How have you been in that scenario? Yeah, so you see it's the same problem. So you want some algorithm that minimizes the overall trouble or work or distance travel before you find your destination, given that it's either behind you or in front of you, to the left or to the right of you. But you don't know exactly how far. And you can only see locally, you can't see globally. So hiking trails, light switches, finding a restaurant or an address or a store or whatever, some landmark. So this algorithm could actually save your life one day. You're on a hiking trail and you're running out of supplies, the sun is setting, and you want to minimize the time it takes you to find the way back, this trail that you forked off from that you need to get back onto. And, all right, how do you do it? What's a good algorithm? Yeah.
This sounds like a lot like the situation in Chan's algorithm where he was trying to find the size of the convex hull.
Okay, so he's referring to Chan's algorithm for convex hull. Let me ask you a simpler question. What's a bad algorithm for this? One that will work for sure, but the complexity is terrible.
To go in one direction and then return back.
Yeah, go one step in one direction. If you don't see the target, go back 2 steps in the other direction, then go 3 steps in the first direction, and go 4 steps in the other direction, and go back and forth and back and forth. How fast is that if you do that? So if what you do is, if here's your wall, and what you do is, you start here, and you go here, and then here, then here, then here, then here, then here, then here.
N to the N.
N factorial.
Twice of n squared.
So I hear n to the n, I hear n factorial, I hear 2n squared. They can't all be right. These are very different answers. All right, how many say n factorial, total distance travel?
I agree with that.
All right, we have n factorial, a few great people. How many say n to the n? Well, at least one person better say it, because you said it to begin with. Okay, never mind, one will do it. You change your mind, it's not gonna change your mind. How many say n squared? Well, we got a few people saying n squared. I'm saying n factorial. All right, we have a split actually, n factorial and n squared. It's interesting because these are very different quantities. One is polynomial, one is exponential. And by the way, n factorial is n to the n over e to the n. So it's not very far off n factorial from n to the n. All right, so you can go back and forth, increasing the distance over time. So in terms of the light switch, you'll be doing this. That's what you'll be doing. Kind of filling the wall a little bit further in each direction every time, one extra foot or centimeter or whatever, inch. So again, n squared, n factorial, what's the total distance traveled there? What was that? Okay, I hear a lot of people murmuring n squared, n squared. How many say n squared? Okay, now we have, how many say n factorial? Okay, now we have a majority on n squared. Anybody want to argue why it's n squared? Say. Let me see if we need to get to the arguments for n factorial.
The final distance is 2n, the maximum that we have to cover, and we're just going back to 1. So it's just sum.
Yeah, so if the thing is, if the total is n, where the true distance to your destination is n, you're going 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7. What are the sum of integers from 1 to n? It's roughly n squared, right? It's n plus 1 times n over 2 or whatever. It's n squared. Sum of integers is n squared. Remember the staircase of the first lecture or the second lecture? The total area of a staircase, 1 unit plus 2 units plus 3 units plus 4 units. Total sum of the areas of all the steps. What was it? Asymptotically. You have n steps, increasing by 1. So I need to show the slides again. You take the staircase, you flip it over, you put it on top of each other. I want to remember that. I hope you'll never forget it as long as you live. It was very visual, very vivid. And then you get a square, a little bit off a square, it's n times n plus 1. But the area is half of that. So anyway, it's quadratic. So the sum of the distances here is quadratic. It's the sum of the staircase. Of course, it's a little bit off because you got 1 plus 2 plus 3. So you got 2 times n there because you got to double back. So you're doubling the n, and on this side, you're also doubling it again. I mean, you can see that. So it's not quite just 1 plus 2, but it's twice or 4 times the sum of integers because you're doubling up every time again and again on both sides. So it's 4 times the area of the staircase, not just the area of the staircase. But that's still quadratic. It's constant times that quadratic staircase. So that's n squared algorithm, not too great. If you're lost in the wild, trust me, you don't want to spend quadratic time out there. You may not survive the experience. Or if you're driving around, you don't want to drive quadratic number of miles instead of a much lesser quantity to your destination. So if you're 10 miles away from someplace, you don't want to drive 100 miles to get to that place that's 10 miles away. In this case, it would either be 4 times 100, 4 times 10 squared. That's huge. You don't want to drive or spend quadratic work if you can avoid it. All right, what's a better solution? let's get other people participating. You already impressed us today quite a bit, so you're good for now. We'll get back to you if they need help. Anybody else? Yeah, okay, increase the distance by power of 2, so you're going double the distance in every direction every time, rather than one more. What would be the total time complexity if you increase your distance by a factor of 2 each time? The total distance would be n log n. How many say n log n? If you double the distance in every direction, back and forth. Let me say something else besides n log n. What else? So let me draw what he's suggesting. So instead of the red path, he's suggesting that you double the distance every time. So he's suggesting this path. He's basically saying double it every time, not just add 1. So how many see this will work in principle? It will correctly find the place of entry. Right. So correctness is not an issue. The question is how fast will it be overall compared to n? Worst case scenario. So we said n log n. I'm going to say n log n. I would say something less than that. Okay. Why n log n? Let's start with that.
So that's log n layers of doubling back, and if we add that up, it's gonna be, I think, basically filling a square by half and half and half and half, then add up to n, so it's gonna be n times log n.
Yeah, so he's arguing it's n log n because it converges, and there's log n layers with log n total trip, number of trips is total log n trips. What do you say?
So, I'm thinking about it visually, so if you have a staircase with the same rate of ascent, when you're going back 1 on 1, if you are doubling it, then you're increasing at an increasing rate, which seemed exponential.
So you think that the total distance will be exponential?
I think that
Well, it's growing exponentially. It's growing by a factor of 2 every time.
so the area under the curve will be less than if it was linear, is what I guess it was.
Okay, less than if it was linear. Well, the total distance traveled can't be less than linear overall because the thing is linear away from you and you have to get there.
Oh, I think what I meant was the linear increase in distance to each side gave you a linear shaped staircase, whereas if you were doubling it, it would increase like that, so the area under that.
Yeah, okay. Somebody else? Anybody else want to? What do you say?
So the total number of trips that you're making
Yeah.
will be proportional to log base 2 of n,
Yes, in proportion to a logarithm, yeah.
and then so you can do a sum over from 1 to log base 2 of n of 2 to the.
Okay, all true. So what is that sum?
I think it comes out to n, but I'm not really sure.
Okay, he says it comes out to n, but he's not sure. Okay, so that's a good intuition. He's saying it's linear. How many agree with him? It's linear.
How did you come up with that?
Okay, what do you say?
I think
Say
if
to them.
you like cut in half, it just becomes simply adding 1 and 1/2 and 1/4, and then it comes to a linear.
Yeah. So what they're saying is that on the very last step, you would have traveled n units to finally get there. On this biggest last step, you would have traveled n units. How many see that? Yeah. On the step before that, how many units did you travel? N over 2. The step before that, how many units did you travel? N over 4. So what's n plus n over 2 plus n over 4 plus n over 8 plus n over powers of 2? 2n. Linear. How do you see it now? Okay. Meta question. Why was that so hard to see in the first place? You don't necessarily have to tell me that, but ask yourself that. Why wasn't it obvious to begin with? So whenever you solve problems, when you finally get a solution, don't just raise your hands and walk away. Do a post-mortem analysis. Go back and do the meta-analysis. Where did you go wrong? Where did you go off the trail? And why was it hard to see? And why was it not obvious to begin with? And kind of do a post-mortem analysis of your problem-solving method. It's called metacognition, thinking about your own thinking, and that will help you solve more problems in the future. Trying to avoid dead ends and unproductive paths. It's a good thing to do. Do an analysis after the fact. So yeah, that's what exponentials do. They converge when you add them. What they converge to is, could vary, but usually it converges to a linear amount if you just add straight exponential. And yeah, there's a factor there of 2 or 4, just like the other path in red, because you're doubling back. So it's 1 plus 1 plus 2 plus 2 plus 4 plus 4 plus 8 plus 8 plus 16 plus 16. So it's twice the exponential. So it's not just 2n, it's 4n. But that's okay, that's still n, that's still linear. So if you're lost out in the woods, and you want to make sure you get home before before dark, or before the end of the week even, well, now you know what to do. Double the distance that you go back and forth. Don't just increase it by a constant amount. When you're driving down the street trying to find your restaurant or whatever it is, now you know what to do. Don't just go one more block each direction. Double the number of blocks you go in each direction. And yeah, you may take 2n or 4n to get there, but it won't be n squared. That's a huge improvement. Any questions about this? Right. Now, when you're stuck behind a big wall and there's the White Walkers coming and winter is here, and now you know what to do. Look for the gate, black castle. I don't even know what I'm talking about. Oh, good. A lot of fans here. All right, nice. All right. Another problem. You have 2 marbles. You want to find the breaking height of a marble. So you can drop a marble from a certain height. You have like a 100-story building, 2 glass marbles. Each marble is identical to the other marble, and they each have the same breaking height. In other words, if you drop them from 3 floors up, they may not break, but if you drop them from 4 floors up, they will both break when they hit the ground. And assume there's no cumulative damage. You can do as many experiments as you want, drop experiments as you want. Your job is to find the breaking height of these 2 marbles. And what do you think you're trying to optimize here? It's a meta question about the question. The number of experiments you perform, the number of drops you make. Because if you only have, say, 1 marble and a 100-story building, and the 100 is really the n here, n is the number of stories. So you want to find the breaking height, that's k, as a function of n. N is the total number of stories guaranteed to break. So if you drop it from the roof, guaranteed both will break. Obviously, you don't want to drop both of them from the same height at the same time, because that's a waste of experiment. If one breaks, the other will break too. They're both identical breaking heights. All right, what's the minimum number of necessary drops if you just have 1 marble and 1 marble only? How many see n? N is required. Why? Because if you drop it from too far of a height and it breaks, the breaking height will be a lot lower, but you'll never know it. And so you won't have the answer. Which means you have to drop it from exactly the breaking height and also from exactly 1 below the breaking height, which means you have to drop it from every single height, beginning with 1. Because if you skip 1 height, if you skip 1 floor at all, it breaks. You won't know if it's that floor or the floor right below it. Of course, how do you see that logic? Okay, that means n is necessary and sufficient for 1 marble. For 2 marbles, what's the answer? We'll get back to you. We don't want to spoil the fun for the other people if they're going to solve it. I'm pretty sure you already know the answer, but what do you say?
You just keep doubling the heights, and then eventually, when it breaks, you go to the height of the drop below that, and then slowly iterate up until you get the height.
Oh, interesting. So it says double the height for the first marble, keep the other marble in store, right, in reserve. Double the height every time, and once it breaks, you just have to find out when it breaks below that height to the previous height, which presumably is half of that, because you doubled every time. And then use the second marble to just climb up one story at a time, one level at a time within that last gap. How many say this is correct, this will work? This will work. How efficient is it in terms of worst case as a function of n, the total maximum number of stories?
Or 2 plus log n.
So at the beginning, what was the answer again?
N over 2 plus log n.
Yeah, n over 2 plus log n, which asymptotically is what?
And
Which is still linear. So asymptotically, this will work, but asymptotically it's still linear. Why? Because that very last jump would be half the size of the building, roughly. And then you have to step the entire way for half the building, which is n over 2, which is still linear. Let me be clear, that's a better answer than one we had before. Because before, it was just n, or n minus 1. Okay. Now it's n over 2 plus log n, which is less than n. Because log n is less than n over 2. So it's definitely an improvement, but asymptotically, it's the same answer, linear. Let's try to do better than that.
Can be log n.
Log n.
You have two, right? First thing, the height, and you said like the first one to 100, the other one to 99. You drop them, say one is broken, you know the time. If it's not, you put them to 50 and 49.
Okay. Any other thoughts? So back to that. So you're saying it's log n asymptotically total? Let's back up. What's the algorithm again that you're using? You're dropping it from the middle,
From the height.
from the top?
Yeah.
All right, if you drop it from the top, it'll always break, guaranteed. Because the building is taller, at least it's taller than breaking height. So dropping it from the very, very top is wasting a marble, because it will break for sure. Yeah.
I think if the number flows is 100,
Yeah.
we try 10 first, with square root of n,
Okay.
and then if it breaks, then we have to travel square root of n.
Okay. Any other thoughts? How many heard what he said? All right, just keep sitting next to him. That's what I'm asking. Any other thoughts? Because he's right. You just didn't hear it. Yeah.
You start with two marbles. The height of one will be twice of the other. So if that one does not break, you can make the height of the smaller marble above this.
Yeah, so if one of them doesn't break, put the one that didn't break.
If both don't break, put the one higher than the height of the other one.
How much higher?
Just one.
Just one? So you're doing this?
So if it's 25 and 50,
Yeah.
the next level would be 51 and 1 or 2.
Okay, but you may end up going 51, 52, 53, 54, and then it's still
No,
linear.
if 1 or 2 is
And then it's still linear. All right, so let me yeah, go ahead, what do you say?
From the previous example, we have intuition, we can walk like n floors, and then we try to shrink the bar. So if we go n one time, the next time we go n minus 1, and then if we're still not broken, we shrink the bar again, go n minus 2, and then et cetera, et cetera.
Okay, but if you go n minus 1, n minus 2, n minus 3, n minus 4, you may end up making a linear number of total drops. So it's back to the linear solution. We're going for something sublinear, asymptotically sublinear, not just by a constant. Because we already reduced the constant by almost a factor of 2 with his solution, n over 2 plus log n is almost a factor of 2 better than n. But we're going for more than a factor of constant improvement. We're going for asymptotically faster. Yeah.
You start in the middle. If you break one, then you move close. N by 4. If it don't
start in the middle, and if it breaks, you go to the lower half. But what if you go to the lower half and it still breaks? Then it's completely ambiguous where below it would have broken if you had more marbles. So nice try, but that won't be giving you the answer. Although it's efficient. But correctness is more important than efficiency. Let me just say. Say the obvious. If you have an algorithm that doesn't give you the correct answer, it doesn't matter how efficient it is. It's not an algorithm for the problem. But still, good try. Trying to do divide and conquer. So yeah, what do you say?
If you divide the building into segments of square root and size, and drop it from top of each, then once it breaks, you go to the section below it.
Yeah,
and it goes
which is
down.
what he said. So he's saying the same thing that this guy said. So you drop the first marble from 10 stories, 20 stories, 30 stories, 40 stories, up to 100. The first time it breaks, you lost one marble, but you still have one more marble. You haven't lost all your marbles. Sounds kind of funny, but you have one more marble left. And then what do you do with the second marble? Let's say floor number 30 didn't break, floor number 40 broke. What do you do with the second marble? Yeah, now you go 39, 38, 37, all the way down to 30. But now you have a small gap to cover linearly. Before that, you had huge gaps. So the size of this gap is what? It's only 10. So the total number of drops is what? Up to 10 to find out which 10-story gap is the breaking height. And then within that gap, 10 more to find out exactly which story within that gap is the second marble. And you know exactly the breaking height. So you spend about 20 drops. Not n over 2, not n. And in general, what's the formula? So it's not just about 10. Why did I say 10? It's the square root of 100. So generally, you have n stories, and break it up into square root midpoints of square root gap size each. And then you spend square root drops to find out which gap you fall into of the breaking height. And then each gap is square root large, and then the second will fill out that gap linearly one at a time, but that's only an additional square root. If you have square root gaps of square root size each. So the total amount of drops is roughly what? Twice the square root. And the square root is asymptotically much less than the linear. It's the square root. Linear is the quadratic of the square root. So the difference between square root and linear is as dramatic a difference between linear and quadratic. How do you see that? Obviously. There's a huge difference when you square something versus when you leave it alone. Huge dramatic difference. A million squared is only a million, but a million is only a million, but a million squared is a trillion. That's a lot bigger. Okay. Any questions so far? Yeah.
Can we generalize this solution if we have 3x or 3?
Yeah. So, what do you think a generalization of this problem would be? So, assuming not everybody heard of it, but that's where it's going. That's always what you should be doing. Generalize the problem, as well as do analysis of why it took you so long to solve it, or what went wrong in your attempt to solve it. And one of the things you should always do is generalize the problem. That's called research.
Well, if you have 3 marbles, is that what
So,
you mean?
increase the number of marbles from 2 to 3 or to 4 or to k. So you have k marbles. Let's say you have 3 marbles.
Then we have cube root.
Then you have the cube root of n.
Yeah, we still have a finite amount after we find out the first interval, and then we just
Yeah,
add square root. So that's
exactly. So now you can see that with 3 marbles, we get an answer for the cube root of n. Yeah, you can. It's true. And with k marbles, you can have a solution that's how fast asymptotically? K marbles? N to the 1 over k, the kth root of n. How many can see that? Yeah. So a hallmark of a good solution is it generalizes pretty straightforwardly and pretty obviously down to larger and larger numbers of marbles. Another possible generalization is try to reduce the constant. So for let me just kind of show you how that might work. So let's say you have 100 stories and, you're going at 10-story intervals. 10 is the square root of 100. It's not exactly what you want to do to get the best constant out of the square root as a product behavior. What do you think you should do instead? So I'm asking you a leading question. Now let's try to squeeze down the constant of the 2 times square root complexity that we had a minute ago. How do you reduce that 2 to something a little smaller? The constant now. To see if you really can dig into this even further. Let me ask you this. Let's say you start dropping the first marble at 10, at 20, at 30, at 40. You may have to do up to 10 drops just to figure out the gap, the 10-story gap. And then you have to go through the gap. So that's 10 more. So that's 10 plus 10. That's what it's 2 times square root of n comes in. But what if it breaks on the first try at the 10th floor? So you spend 1 drop, you realize it breaks floor number 10. How many more drops do you need to do to figure out the exact breaking height? About 9 more. So that's 1 plus 9. So in 10 steps you'll be done. That's not 2. That's square root. That's not 2 square root. What if it breaks at 20? Not at 10, but at 20. So you took 2 drops to get to 20, and now it breaks. So now you have to go about 9 more drops to get from 19 to 18 to 17, all the way down to 11. That's about 10 more. So it's 2 plus 10. How many can see that? So on the low end, you're doing a lot less than 2 times square root of n. You're doing roughly square root of n plus 1, square root of n plus 2, plus 3, whatever it is. Only at the very, very far end will you need to do the square root drop to find the gap, and then square root more to find within the gap where you are. So where is the optimization here?
If we can just find the minimum number of n over k plus k, or if you know the probability of it breaking at each stories, you can also map the probability distribution to that.
Yeah, so he's mentioning probabilities. Let's not worry about probabilities right now, because that's even more complicated. Let's just worry about worst case scenario.
The minimum number of n over k plus k, right?
Yeah, so the first try shouldn't really be from story number 10. Why not? Why shouldn't it be from the 10th story? Because if it breaks, you just need 9 more to figure out the exact height of the second marble. And you're still way below 2 square root of n. You're at really square root of n plus 1, or square root of n. Let's go to square root of n plus 1. So what should you have done on the first try? Should you have gone to story number 10, drop from there? Let me ask you this. What if you got to story number 15 and dropped from there and it broke? So that's 1.5 square root height, or 15 instead of 10. And if it broke, you just need to do how many more? About 14 more, and the total is 15. That's still a lot less than 20. How many see that's better? So you shouldn't do it just from square root of 10 and another square root of 10, or square root of 100, or 10, and then 20, and then 30. The first drop should be roughly from height 15 or 16 or something like that. Never mind exactly what it should be. And then the second drop should be from what story? You went 15 up the first time, 14 up the second time, and 13 up the third time. And at the end, you won't have to do square root of n, because you're jumping in increments of more than the square root of n, so you have to do less than the square root of n increments before you get to the root on the first marble. How you see the optimization here? And then reduce the constant. And I'll leave it up to you for extra credit to figure out exactly how much that would reduce the constant in a general case, and what's the general strategy. Any questions about that? And you can think about other generalizations. All right. Are we good on all this? Another interesting problem, unwritten problems. This can come up in interviews, by the way, and these kind of questions do come up in interviews. So when it comes up in an interview, don't blurt out the answer right away. Pretend to think a little bit, and then give it the answer. They'll really be impressed. And I'll just take 10% of the salary. Not asking for much. Just kidding about that last part. All right. What other problems are interesting here? What about this problem from the homework? So you want to randomly permute an array. Let's say you have a perfect random number generator. So a random number ij returns a random integer with equal probability of all the integers between I and j, I not being equal to j. Actually, in fact, I to be equal to j, and then just get I back, or j back to equal. So uniform, so there's nothing wrong with the random number generator. But from it, you're trying to construct a random number permuter, trying to construct a random permutation of an array. So this piece of code tries to do the job. I goes from 1 to n, you just swap ai with a sub random between 1 and n, and there's only n integers in the array, and this will scramble the array. So how many see this will scramble the array? Obviously. But the question suggests that it won't scramble it with equal probability. Some permutations will be more likely than others. How many can see that? All right. Only a few people. Let me not be presumptuous. How many worked on this problem? Oh, good. So a lot of you worked on that. That's 90% of the win is right there. So I appreciate that. A lot of you worked on it. That's nice. If you didn't work on it at all, I'm not sure what you were waiting for, but never mind that. So, first of all, what's wrong with this permutation generator? Why does it not create all permutations equally likely? So again, the algorithm here is permuting the array by exchanging the ith element, for every I, with a random element of the entire array. You just do the swap. So we swap a pair with I being one of them and a random other element from the entire array being the other element. And we just keep doing that for every element. At the end, hopefully it's all scrambled. But it's not equally probable scramble. Some permutations will be much more likely than others. Why? What do you say? Back there. Yeah, what do you say? Yeah, so the total number of possible different outcomes from this piece of code, assuming that the random number generator function, the random one, and this guy here, the random permutation, random number generator works perfectly. The total number of outcomes from this piece of code is what? N to the n different possible outcomes, right? Executions, different executions. And if this generates equally probable permutations, then every permutation has to correspond to one of those executions, and it sort of does. But these executions can generate the same permutation even though they're two separate executions. So for example, if I have only two elements, first thing I can swap the first with the second, and I'll get this. Then I can swap the second with the first and get that back. Obviously that can happen. So some permutations can happen in several different types of execution. Or I could have executed another execution, exchange the first with the first, then exchange the second with the second. In other words, leave them alone. And you get, again, the same identity permutation that you started with. Or I could have swapped it twice. So different executions can end up with the same permutation. But for the permutations to be equally probable, the number of executions better be evenly divisible by the number of permutations, otherwise not all permutations will be equal. How many see that? Must be equally divisible. So let's take a simple case, only 3 elements. Element 1, element 2, element 3. How many executions are there if there's a 3-element array here? 27, 3 to the third. I mean, you see 27 different executions for 3 elements. Yeah, exactly. How many permutations are there on 3 elements? 6, 3 factorial. That's 1 times 2 times 3, that's 6. Does 6 divide even into 27? No, of course not. So out of these 27 permutations, 27 executions, some permutations will be hit more than other permutations because the two don't divide evenly into one another, 27 and 6. And in general, it's not true that n to the n will divide evenly by n factorial. They just won't in general. So there's something very wrong with this piece of code. It'll make some permutations much more likely than others, and that's not what we want. That's not a true permutation, random permutation generator. It's flawed. It's skewed. It's like having a biased coin. You have a biased coin and you flip it. Ideally you want 50-50 chance heads or tails, equal numbers. What you don't want is a 90-10 probability of heads and tails. Then something is very fishy about that coin. And if you play dice, you better have 1/6 probability of coming out any particular number. If it always comes out 6s, don't play against whoever's giving you that dice. In fact, don't gamble anyway, it's my personal recommendation. But if you do, make sure it's a fair game, so you're not getting cheated. So it's fatally flawed, this permutation generator, random permutation generator. Even though the random number function was perfectly fine. You just used it badly in this piece of code, which is interesting. There's nothing wrong with the random number generator that you're using as a subroutine. That's not the problem. That would work perfectly. Sometimes even that's flawed, and that's a separate issue. But even assuming that's perfectly valid, works as advertised, equal probability for random numbers out of that function, you're using it in a way that makes the whole permutation generator flawed. Any questions so far? How many can see all that? Good. Okay. Good. Next question. How do you fix it? How do you fix this permutation generator so that all permutations are equally likely? What's your new algorithm? Because obviously this one is not working with equal probability. It's skewed. Like a bad dice. Like a cheating dice or a cheating coin. How do you fix it? Maybe somebody new. The same 3 or 4 people keep impressing me, and I appreciate that, and it's great. But I want to give other people a chance to speak up and feel the rush and be a hero. Yeah.
Can we swap with I plus 1 and 2 and elements instead of from use a random between I plus 1?
Yeah. So he's saying when you swap, don't swap from 1 to n. Swap from I to n. Yeah, I'm not sure how to get the pen to work, but the swap, make this random, not from 1 to n, but from I to n. Make that 1 an I. I tried to change that 1 to an I on the slide, but it won't let me. So I'm just telling you, make that 1 an I. So you're swapping the current element with any of the elements in front of it, not behind it in the array. Not from 1 to n, but from I, from this current location to n. How many see that change will get you a lot better results? How many see why? Less people than believe that it would be good. Okay, what's the argument to why is this working? Why is it equal probable?
Could be turning into n factorial
Yeah, now there's n factorial outcomes or executions out of this piece of code from I to n, not from 1 to n. So at the end of the n execution, there's n factorial execution. How many see that part? Yeah. And every possible permutation can happen. No permutation will be left out in a way that's impossible to achieve it from this new algorithm. How many can see that? Yeah. And so because there's n factorial different outcomes and n factorial permutations and they're all possible, they'll all be hit with a single execution, a unique execution. You wouldn't have a case anymore that multiple executions give you the same permutation. And they're all possible, not all left out, which means they're equally likely. Because all the executions are equally likely. And now it's fixed. And now we don't have this fatal flaw. Very minor change. Very big difference. Probabilities are tricky that way. Any questions about that? Yeah.
Would the likelihood that an element is swapped be greater for elements later in the array than elements earlier in the array?
With a new algorithm, the likelihood will be the same. Yeah. Because for every element, you either swap it with something or you don't swap it with something. And if you swap it with something, it can be swapped with anything. Forward in the array, or before that, it could have been swapped with something earlier in the array. All right. We talked about dice and coin. Let's say you have a biased coin. You're playing some gambling game with flipping coins and you earn money based on heads or tails. Same with dice. Let's say you have a loaded dice. It's skewed. It's not 160. The probability of different numbers coming out. Let's say you have a coin, simpler case. So the coin is not 50-50. But you don't know what it is. You just know it's a bad cheating coin. So it could be 40-60, it could be 70-30, it could be 90-10, it could be 99-1, then it's really obvious that it's a bad coin. Almost always comes up close. But you know it's not 0-100, there's not heads on both sides of the coin. Tail is possible, the head is possible, but you know it's not 50-50. You just don't know what it is. But you know it's a fixed skew. The skew doesn't change over time. How can you still play a fair game with a skewed coin, with a biased coin? 60-40 or 70-30 or whatever it is. Let's call it P, 1 minus P. Or P is not 0. P is between 0 and 1. So the probability of skewness is P. But P is not 50. It could be 30 or 70 or 90 or 1 or 3 or pi. It could be a rational number. So you have a P, 1 minus P skewed biased coin. How do you use it to still play a fair game? And by the way, how many can see that this, whatever the answer is here, could be easily applied in algorithms and in code? Because you can have a random number generator and a skew. And you don't know the skew, you just know that it's a fixed skew. And you can use this, with the solution we're about to show, to use a random number generator, the skewed one, the biased one, in a way that's unbiased. So you can convert a biased one to an unbiased one. In other words, you can remove a bias from a random number generator without even knowing what the bias is. And that's a tall order. It sounds almost impossible to do. How do you do it? Again, let's get some new people, and if we don't get an answer, we'll get back to those who know all this. Yeah.
You can make each person try same times of attempts and compare the times of heads.
Okay. Any other thoughts? He's on the right track. Assuming not everybody heard him, what do you guys say? What do you say?
They twice swap the loops.
Yeah. So flip the coin twice. So flip it twice. So you flip it twice, you can have heads, tails, tails, heads, or tails, tails, and heads, heads. Right? That works. So you can have these 4 cases. Heads, tails, tails, heads, tails, tails, heads, heads. And so you flip it twice. What do you do next? So you flip the bias coin twice. How do you get a single unbiased flip from a double biased flip? At this point, it's straightforward.
I think the probability of heads tails is the same as the probability
Yeah.
of tails heads.
So the two probabilities of heads tails and tails tails, heads tails and tails heads is the same. What is that probability, by the way? P times 1 minus P. They're both the same probability. How many can see that? Yeah. These two probabilities are not the same. Because this will be P times P, this will be 1 minus P squared, this will be P squared, and you don't know what P is. So it's hard to do work with those two. So flip it twice. If it comes out this guy versus this guy, what do? Not hard at this point. What do? You flip it twice, let's say it's this, heads, tails.
Why? Return anything. Return heads.
Yeah, call this the new heads. Call this the new tail. So flip it twice, if it comes out this, call that a head. If it comes out this, call that a tail. How many see what's going on now? And you'll be doing that with equal probability. P times 1 minus P, without even knowing P. This will be true. What if it comes out one of these other two? Ignore it. Keep going. Do it again. How do you understand the solution? That's how you remove bias from a biased coins without even knowing what the bias is. This just works beautifully. It's simple. Any questions about this? This problem and its solution was originally proposed by John von Neumann back in the 1940s. On the work of probability and random number generators, things like that. Yeah.
I guess the prerequisite for this is that P has to be greater than 0, right?
Yeah, so now he's getting into the weeds. So if P is 100, this won't work. How do you see that? Yeah. But if P is 100, what you have is not a biased random number generator. You have a variable as a constant. So you can't turn a constant into random numbers out of magic from thin air, because that will greatly increase the entropy of the situation. And entropy is very tricky business. You can't just arbitrarily increase it. It turns out that generating true random numbers, or even recognizing true random numbers when you see them, is an undecidable problem. There's no algorithm in the universe, you can prove that can detect random numbers even when it sees them, never mind generating them from scratch. That's even harder. That's doubly undecided. This is, of course, in theory, we would prove it right here and now, but it's, of course, an algorithm, so just trust me on this for now. For extra credit, prove it to me. Okay, so P can be 1, and it can be 0, and it can't be 100. Otherwise, you don't even have a random number function that's biased, because it's not even a random number function. Never mind biased or unbiased. It's just a constant. It's always heads or always tails. How many of you have ever seen the movie Gilderstein and Rosencrantz Are Dead? It's about a couple of minor characters that Shakespearean Hamlet play, except it's not about Hamlet. Hamlet's in the background, saying to be or not to be. But he's way in the background. It's about these two minor characters instead. And they feel they're trapped in a novel or a play, and it's predetermined. And from the plot, you know what's going to happen to them. They're not going to survive the play. Because in the original Hamlet, they appear and they do get executed. But the way they're trying to figure out if it's predetermined or not, they flip a coin. It's an unbiased coin, or at least they think it is. And it always comes out heads. And that's when it dawns on them that this is not reality, this is predetermined, just like the Matrix. It's predetermined, and it's not truly random, and they begin to worry more and more about their fate. And justly so. Anyway, if you ever seen that play, it's a beautiful take on Hamlet, kind of inverted and de-randomized. But random numbers are a very deep subject, and randomness in general, and entropy, very, very deep computer science of randomized algorithms, the power of randomization. It's beautiful stuff. How efficient is this? Because you have to throw away a lot of double T's and double H's. And you have to throw them away with probability, p squared of 1 minus p squared, whichever is greater. So you end up throwing away a lot of trials, and sometimes if p is very skewed, if p is 99, or 1 equivalently, it'll be a long time before you can generate a head or a tail. How many can see that? Yeah. So the next question, which you want to answer here, is how many iterations do you have to do as a function of p, the probability, to get a head or a tail in green versus throw away these double tails and double heads and create waste? And I'll leave that up to you as an extra credit problem. Any questions about that? I mean, you can see that's an issue. The more skewed p is, the less efficient this way of de-randomization or removing bias works. Works less efficiently if p is more and more skewed. And that's true. And then beyond that, once you figure out how many times you have to waste away flips and throw them away and ignore them before you can generate true heads and tails in green, figure out a way to improve upon that, make it more efficient yet. And that's yet another problem beyond that. But for now, we'll leave it here. Any questions about anything we've done today? We solved a bunch of interesting algorithmic problems. We showed elegant solutions for each. Whenever you solve problems, try to go back and do post-mortem analysis, figure out what went wrong in your tries, where you went awry, what dead ends you reached and why, and in the future you'll do less of that and more productive kind of forging forward, going into productive lines of thinking. But you gotta actively do all this. Solve lots of problems and do lots of these kind of post-mortem analysis of what happened while you were trying to do this meta-cognition beyond the actual problem. So, Polya talks about all of that in his book, How to Solve It. George Polya. How many read that book by now? Good. If you haven't, I'm not sure why you're doing yourself this service by not reading that book. It's a great book, it has all this stuff in it. All right. See you next time.